Dear students, welcome to this session on the topic scoring matrices. First of all, let us have a look into the basic concept of a scoring matrix. New biological sequences are being generated at different laboratories all over the world, and the sequence database is growing at an exponential rate. Comparison of these sequences with other sequences is very essential for its characterization. Sequence comparison is also important in drawing functional and evolutionary relationships with other sequences. In the case of proteins, sequence patterns, structural motifs and folds can be identified by comparing the sequences with that of other known proteins in the databases. During the comparison, one-to-one correspondence of the residues of two or more proteins are being established, and it is generally known as the sequence alignment. DNA and proteins are products of evolution. Over the period of time, the molecular sequences undergo random changes or mutation, and some of which are selected or accepted during the process of evolution. As the mutation is random and independent, divergent sequences are evolved from an ancestral sequence. The information regarding the ancestral sequence remains hidden in the current sequences and can be traced back by simulating the evolution. This permits us to find out the common ancestry of different sequences. Some residues that perform key functional and structural roles tend to be preserved by natural selection, as the mutation of these residues may lead to loss of the function of the protein. Other residues that may be less crucial for structure and function tend to mutate more frequently, as the mutation of these residues may not affect the function of the protein. By comparing sequences after alignment, patterns of conservation and variation can be identified. The degree of conservation of sequences reveals the evolutionary relationships of different sequences, whereas the variation between sequences reflects the changes that have occurred during evolution in the form of substitution, insertions and deletions. The correspondence between the two aligned sequences can be expressed in terms of similarity or identity score. The alignment score is a function of the identity or similarity between the aligned residues and the gaps introduced to align the sequences. The alignment procedure makes use of a scoring system, which is a set of values for qualifying the likelihood of one residue being substituted by another during the evolution. The scoring system is called substitution matrix and is derived from statistical analysis of residue substitution data from sets of reliable alignments of highly related sequences. A scoring matrix implicitly represents a particular theory of evolution. Scoring matrices for nucleotide sequences. Scoring matrices for nucleotide sequences are relatively simple. A positive value or higher score is given for a match, and a negative value or low score for a mismatch. This alignment is based on the assumption that the frequencies of mutation are equal for all bases. However, the observations show that transition or substitution of a purine by another purine or a pyrimidine by another pyrimidine occurs more frequently than transversion, which is substitution of a purine by a pyrimidine or a pyrimidine by a purine. Therefore, a more sophisticated statistical model with different probability values to reflect the two types of mutations are used to frame matrices for nucleic acids. The DNA matrix incorporates ambiguous DNA symbols like R for A or G, which are purines, and Y for C or T, which are pyrimidids, and information from mutational analysis which reveals probability of transitions and transversions. A series of nucleic acid PAM matrices based on a Markov transition model was designed to improve the sensitivity of similar searches of sequence database and can be used to score nucleic acid alignments. A Markov model is characterized by a series of changes of state in a system such that a change from one state to another does not depend on the history of previous changes. Now, let us see nucleic acid PAM matrices. A series of nucleic acid PAM matrices where PAM stands for point accepted mutation based on a Markov transition model was designed to improve the sensitivity of similar searches of sequence database which can be used to score nucleic acid alignments. PAM matrices are based on certain assumptions that evolution at each site occurs according to a simple or first order Markov process. Next mutation depends only on the current state and is independent of previous mutations. Mutation probabilities are given by a substitution matrix M equal to mxy, where mxy is the probability of x to y mutation, which is probability of y by x, for a model in which all mutations from any nucleotide to any other are equally likely and in which 4 nucleotides are present at equal frequencies. In table 2.1, the diagonal elements represent the frequencies for the substitution of a nucleotide by the same nucleotide equivalent to no change, while the other elements represent frequencies for the substitution by a nucleotide by any other nucleotide. The values for 4 diagonal elements of the PAM1 matrix are 0.99, whereas the 6 other elements are 0.00333. Table 2.1, you can see the nucleotide mutation matrix for an evolutionary distance of 1 PAM, which corresponds to a probability of a chance at each nucleotide position of 1%. The values are chosen so that the sum of all possible changes for a given nucleotide in the PAM1 matrix is 1%, which is calculated as 3 into 0.00333 equals 0.00999, which approximately equals 0.01, which is equal to 1%. These values are then used to produce log odds scoring matrices that represent the frequency of substitutions expected at increasing evolutionary distances. Table 2.2 form these PAM1 matrices. Additional log odds matrices at an evolutionary distance of n PAMs may be derived by multiplying the mutation matrix by itself n times. In table 2.2, you can see a nucleotide substitution matrix at 1 PAM of evolutionary distance. Now, let us see the scoring matrices for amino acids. Since there are 20 amino acids, the scoring matrices will be having 20 columns and 20 rows. There are essentially 2 types of amino acid substitution matrices. One type is based on interchangeability of the genetic code or the physiochemical properties of amino acid, and the other one is derived from the empirical studies on amino acid substitutions. It has been proved that the empirical approach is more accurate than the first method. The substitution matrices apply logarithmic conversions to describe the probability of amino acid substitutions. The converted values are logarithmic ratios of the observed mutation frequency divided by the probability of substitution expected by random chance. Empirical matrices, which include PAM and BLOSUM matrices, are derived from actual alignment of highly similar sequences. By analyzing the probabilities of amino acid substitutions in these alignments, a scoring system is developed by giving a high score for a more likely substituent and low score for a rare substitution. For a given substitution matrix, a positive score means that the frequency of that substitution is greater than that would have occurred by random chance. Substitutions of identical residues or very similar residues will have a very high score. A 0 score means that the frequency of amino acid substitution found is equal to that expected by chance. In this case, the relationship between the amino acid is weakly similar at best in terms of physiochemical properties. A negative score means that the frequency of amino acid substitution is less than that would have occurred by random chance, and the amino acid will be dissimilar in physiochemical properties. Substitutions by similar residues are likely to preserve the structural and functional features of the proteins, while substitution by an amino acid differing in physiochemical properties are more likely to cause disruption to the structure and function and is less likely to be selected in evolution because it renders non-functional proteins. For example, phenylalanine, tyrosine and tryptophan share aromatic ring structures, and because of their chemical similarities, they are easily substituted for each other without perturbing the regular function and structure of the protein concerned. Hence, substitutions by amino acids similar in physical and chemical properties are more likely to be observed in mutations accepted by natural selection. Cysteine has a role in metal binding, disulfide bond formation, and as an active site residue in many enzymes. Substitution of cysteine with other residues often abolishes the enzymatic activity or destabilizes the protein structure and hence very less likely to be observed. Now, let us see PAM matrices for amino acids. PAM matrices are amino acid substitution matrices or scoring matrices used in comparing protein sequences that encode and summarize expected evolutionary change at the amino acid level. The term PAM is an acronym for Point Accepted Mutation or Percent Accepted Mutations. It is used as a unit to measure the amount of evolutionary divergence or evolutionary distance between two amino acid sequences or proteins. In that context, one might say that sequence S1 is 5 palm diverged or 5 palm distant from sequence S2. The elements in the matrix refers to the chances of the given amino acid substitutions. The methodology of PAM units and the first PAM matrix were developed by Margaret Dayoff and co-workers. They aligned 71 groups of very closely related protein sequences. Because of the use of very closely related homologs, the observed mutations were not expected to significantly change the common function of the proteins. Thus, the observed amino acid mutations are considered to be accepted by natural selection. These protein sequences were clustered based on phylogenetic reconstructions using a technique called maximum parsimony. The PAM matrices were subsequently derived based on the evolutionary divergence between sequences of the same cluster. This allows computation of ancestral sequences for each internal node of the trees. Ancestral sequence information is used to count the number of substitution along each branch of a tree. A PAM unit is defined as 1% amino acid change or 1 mutation per 100 residues. To construct a PAM1 substitution table, a group of closely related sequences with mutation frequencies corresponding to 1 PAM unit is chosen. Based on the collected mutational data from this group of sequences, a substitution matrix is derived. The PAM score for a particular residue pair is derived from a multi-step procedure involving calculations of relative mutability, which is the number of mutational changes from a common ancestor for a particular amino acid residue divided by the total number of such residues occurring in an alignment. Normalization of the expected residue substitution frequencies by random chance and logarithmic transformation to the base of 10 of the normalized mutability value divided by the frequency of a particular residue. The resulting value is rounded to the nearest integer and entered into the substitution matrix, which reflects the likelihood of amino acid substitutions. This completes the log odds score computation. After compiling all substitutions, a 20-20 palm matrix is generated. Use of the Markov model makes it possible to extrapolate amino acid substitutions observed over a relatively short period of evolutionary time to longer periods of evolutionary time. Palm matrices with increasing suffix numbers for more divergent sequences can be extrapolated from palm 1 through matrix multiplication. For example, palm 80 is produced by values of the palm 1 matrix multiplied by itself 80 times. Each palm matrix is designed to be used to compare pairs of sequences that are a specific number of palm units diverged. For example, the palm 120 matrix is ideally used to compare two sequences known to be 120 palm units diverged. For any specific pair of amino acid characters denoted AIAJ, the ij entry in the palm n matrix reflects the frequency that AI is expected to replace AJ in two sequences that are n palm units diverged. In this figure, you can see an example of a Dayhoff palm 250 matrix. Amino acids are grouped according to the chemistry of the side group in this figure. Each element of the matrix is calculated by first dividing the frequency of change for each amino acid pair in related proteins separated by one step in an evolutionary tree by the probability of a chance alignment based on the frequency of the amino acids. The increasing PAM numbers correlate with increasing PAM units and thus evolutionary distance of protein sequence. For example, PAM 250, which corresponds to 20% amino acid identity, represents 250 mutations per 100 residues. Accordingly, PAM matrices with lower serial numbers are more suitable for aligning more closely related sequences. Now, let us see in detail BLOSUM matrices. BLOSUM stands for block substitution matrices. It was first calculated by Gorjaji Henikoff and Henikoff Steven in the year 1992. This series of amino acid substitution matrices were derived based on the direct observation for every possible amino acid substitution in multiple sequence alignments. These were constructed based on more than 2000 conserved amino acid patterns representing 500 groups of protein sequences. The sequence patterns, also called blocks, and are ungapped alignments of less than 60 amino acid residues in length. The frequency of amino acid substitution of the residues in these blocks are calculated to produce a numerical table or a block substitution matrix. Instead of using the extrapolation function, the elements in BLOSUM are actual percentage identity values of sequences selected for construction of the matrices. For example, BLOSUM 62 indicates that the sequences selected for constructing the matrix share an average sequence identity of 62%. Other BLOSUM matrices based on sequence groups of various identity levels have also been constructed. As opposed to palm numbering system, the lower the value of suffix or BLOSUM number, the more divergent sequence they represent. The BLOSUM score for a particular residue pair is derived from the log ratio of observed residue substitution frequency versus the expected probability of a particular residue. The log odds is taken to be the base of 2 instead of 10 as in the PAM matrices. The resulting value is rounded to the nearest integer and entered in the matrix. As in the PAM matrices, positive and negative values correspond respectively to substitutions that occur more frequently and less frequently than random substitutions. The values of the BLOSUM 62 matrices are shown in this figure. Here you can see the amino acids in the table are grouped according to the properties of the side group. Each entry is the actual frequency of the occurrence of the amino acid pair in the blocks database clustered at the 62% level divided by the expected probability of occurrence. The expected value is calculated from the frequency of occurrence of each of the two individual amino acids in the blocks database and provides a measure of a chance alignment of the two amino acids. The actual or expected ratio is expressed as a log odd score in the so-called half bit units obtained by converting the ratio to the logarithm to the base 2 and then multiplying by 2. A 0 score means that the frequency of the amino acid pair in the database was as expected by chance. A positive score that the pair was found more often than by chance, and a negative score that the pair was found less often than by chance. The accumulated score of an alignment of several amino acids in two sequences may be obtained by adding up the respective scores of each individual pair of amino acids. The highest scoring matches are between amino acids which are in the same chemical group, and the very highest scoring matches are for cysteine-cysteine matches and for matches among the aromatic amino acids. The Blossom 62 matrix gives a more positive score to mismatches than the rare amino acids. Example, cysteine, a more positive score to mismatches with hydrophobic amino acids, but a more negative score to mismatches with hydrophilic amino acids. Here is the overall procedure to develop a Blossom X matrix. First, collect a set of multiple alignments. Find the blocks with no gaps. Group the segments of blocks with X% identity. Count the occurrence of all pairs of AAs and employs these counts to obtain odds ratio or log. Differences between distance and similarity matrix. There are important differences in the ways that the Palm and Blossom scoring matrices were derived, and these differences should be appreciated when interpreting the results of protein sequence alignments. A scoring matrix implicitly represents a particular theory of evolution. Elements of a matrix specify the weight to be assigned for a given sequence in comparison during an alignment. When weight to be assigned is quantified by the measure of similarity for replacing one residue with another, the matrices is termed as similarity matrices. When the weight to be assigned is quantified by the measure of cost of replacement of the residue with one another, is termed as distance matrices. The distance score D is usually calculated by summing up of mismatches in an alignment divided by the total number of matches and mismatches, which represents the number of mutations required to change one sequence into other, ignoring gaps. Thus, D equals matches by total number of matches plus mismatches. Less similar the sequences, greater the distance score between them. Similarity matrices like Blossom have more advantage in searching databases and finding conserved domains in proteins, while distant matrices like Palm N were derived from an evolutionary model and are used more often for constructing phylogenetic trees. Now it is time to summarize the session. Pairwise sequence alignment is extremely useful for finding out structural, functional and evolutionary relationships between sequences. To quantify the alignments, one need to make use of scoring matrices. Scoring matrices describe the statistical probabilities of one residue being substituted by another. Palm and Blossom are the two most commonly used matrices for aligning protein sequences. The Palm matrices make use of evolutionary models and extrapolation of probability values from alignment of close homologues to more divergent ones. In contrast, the Blossom matrices are derived from actual alignment. The serial number n in palm n and blossom has different meaning. Matrices of high palm numbers are used to align divergent sequences and low palm numbers to align closely related sequences. One would use a higher numbered blossom matrix for aligning two closely related sequences and a lower numbered matrix for divergent sequences. However, no single matrix is the complete answer for all sequence comparisons. Each matrix has its own advantages and disadvantages. Before we move to the next session, please try to answer the following questions. First, describe briefly what are scoring matrices and how they are constructed. Second, compare palm and blossom series of scoring matrices. References: Introduction to Bioinformatics by Atwood and Parry Smith, Pearson Education. Structural Bioinformatics by Philip Bond and Helge Wiesing by Wiley. Bioinformatics Methods and Applications, Rastogi, Mendeletta and Rastogi P. Prentice Hall of India Private Limited, New Delhi. Essential Bioinformatics, Jin Zhong, Cambridge University Press. Hope the session was useful to you. See you next time. Bye.